Hello, my name is Li Pan Jing, metric number AE230052. Now I will present about the result for the question 1. So for the question 1, part A, design the circuit to obtain an overdamped, critical damped, and underdamped response. For the design, choose the underdamped frequency omega in the range of 100 to 1000 radian per second. So we are choosing the underdamped frequency omega equals to 400 radian per second. So for the first one is the under dam. So this is the manual calculation. And then we will get this result for the under dam response and verify it. And we will show that this is the over dam response. So this is the circuit for the over dam circuit. And then the next one is the critical dam. So this is the manual. And then we will get this result for the critical dam response. So we verify it. Then we will show that this is a critical dam response. So this is the critical dam circuit. And then finally the under dam response. So this is the manual calculation. And then we will get this result. And then we verify it and it show that it is under dam response. So this is the under dam circuit. So for the part B, the expression of the VCT and ILT for the t greater and equal to 0 second for each of your circuit design in part Q1A and show all your calculation. So for the overdamp response, this is the value outside that, and then calculate using several method, and then we will show that the ILT expression for the overdamp response is this. VCT expression for the overdamp response is this, and then critical damp response, manual calculation, and then we will get the ILT expression is this for the critical damp response, and the VCT expression is this for the critical damp response. So the last one is the underdamped response. This is the manual calculation. So the ILT expression for the underdamped response is this, and then the VCT expression is this for the underdamped response. So the next one is the stimulate the circuit design in part Q1A and plot all the response of VCT and ILT for t greater and equal to 0 second. So we are using the Proteus. So this is the circuit and this is the graph. So we are putting this inside the graph. And then we stimulate the graph, and then we will get these three graphs. So for the first one is the blue line, which is the underdamped response. So the underdamped response have oscillating before reaching the steady state. So for the red line is the critical damp. So the critical damp response is without oscillating, and then is the faster within these three reaching the steady state. And then the last one is the overdamp. So overdamp also without oscillating and reaching the steady state. So according to the speed, so the first one is the critical damp, second one is the underdamp, and the last one is the overdamp. So there is a question Q1D asking for the shorter time on reaching 80% on the final value for the VCT. So it is the critical damp response, which is the red line, which is this. So for the next one is the ILT. So putting all these inside. And then simulate the graph. So this is the three graphs. So for the blue line, we also see that there is a oscillating and then reaching the steady state, which is the 8 ampere. Sorry, is 8 ampere. So it is oscillating and reaching the steady state 8 ampere. So For the critical then, which is the red line, so it is without oscillating and reaching the steady state, which is the 8 ampere. And then the last one is the overdam, which is the green line. So it is also without oscillating and reaching the steady state. So we can see that the red line is the faster and the green line is the slower. So according to the speed, so the first one is the critical dam response, which is the red line, and then the second one is the under dam response, which is the blue line. The last one is the green line, which is the over dam response. And that's all from me. Thank you.
Hi, my name is Wong Chun Yu, matric number AE230063. Now I would like to present the question 2. The question 2 asking to find IA, IB, IC, and BT. Our group decide to use the first nodal analysis and second method is superposition theorem. For nodal analysis, we setting the node as V1, V2, and V3. And then lastly, we will get the answer IA, IP, IC, and also VT. So same with the second method, for the superposition theorem, we will use one source at one time. For the voltage source, we will short circuit, and for the current source, we will open circuit. And then lastly, we will combine the value of two source. And then lastly, we can also get the same answer with the IA, IP, IC, and also VT. And now is the simulation part. We design the same circuit as the given question. And now we will find the IA, IP, IC, and also VC. We put the node A for the current and V for the voltage to find the current and voltage. And so this is the result of our simulation. We can show that the simulation result is almost same with the calculation result. And then now we will see about the graph. This is the first graph, which represent the IA. This one is the graph represent the IB. This one is for IC, and this one is for the VC. And for the graph IB and also the VC, we can show that there's a little bit decreasing amplitude over the time. This might be because the residual transient effects that haven't fully damped out. In the purely steady state AC analysis, the current and voltage should oscillate with the constant amplitude. And also, this might be result from the initial energy stored in the reactive components dissipating through the resistive elements over the time. So these two might be the reason why the graph is decreasing the amplitude. And next, for the graph of IC and also the VC, we can show that the amplitude of the graph is slightly different with the calculation result. The mismatch is happened due to the phase difference and the impedance effect within the RLC circuit. The varying impedance of each component with the frequency affects the amplitude and the phase of current and voltage. The interaction between the inductor and the capacitor and the phase shift they produce lead to complex time varying responses. This causing the observed amplitude mismatch until the system reach its steady state. And that's all for our presentation. We are from Group 8. Thank you.